Welcome back to the video series on integration and differential equations. Today we're going to discuss volume by double integration. So we're going to be working in 3D. I'll draw the X, Y, and Z axes. We'll have some surface Z. Let's just draw it like that. Let's say that's our surface Z. And we'll have some region of the XY plane. For example, we might have, say, a triangular region. So let's call that region A. And what we'll be trying to calculate today is the volume under the surface Z over the region A. So let's try to make sense of that in the picture. So the region A, it's a triangular region within the XY plane. And what we want to do is draw some lines perpendicular to the XY plane that intersect the boundary of this region A. Okay, so we're going to draw some lines straight up until they hit our surface. So we could draw another line straight up here, maybe it would hit the surface right there, and then another line perpendicular to the XY plane. So these lines that we've just drawn, they form the boundary of the volume that we're trying to calculate. And if I were to shade in the volume, I'll just shade it in lightly so that we can still keep some perspective here. You can see that we've created a three-dimensional solid, and we'd like to try to calculate the volume of that solid. So the base of the solid is given by that region A that we had at the start of the problem, and the top of the solid here is formed by whatever surface Z we're working with. So I should point out, just to clarify the picture, that the base here is going to be completely flat. The base is sitting in the XY plane, whereas the top may be very curvy because we're talking about a surface in 3D here that's forming the top boundary of that volume. Okay, so let's make a connection between volume and double integration. The way that we're going to calculate the volume is by taking a double integral. What we're going to be integrating is Z, so that's the formula for our surface, and then we'll integrate with respect to Y and then with respect to X. To figure out what limits to put on the double integral, for now I'm just going to write A, meaning we will integrate, do our double integration over whatever region A is appropriate for the problem. Just a side comment here, occasionally when we do the volume calculation, we'll have the opposite order of integration. So sometimes it'll be the case that we'll integrate with respect to X first. Remember that we always start with the inside integral. So occasionally we'll integrate with respect to X first and then integrate with respect to Y. But most of the time we'll be using this top formula here. More natural in most cases to integrate with respect to Y first. So we'll see all these details as we jump into our first calculation. For our example today, we're going to find the volume under the plane x plus y plus z equals 2 in the first octant, where x, y, and z are all non-negative. So I should point out here that the x, y, and z axes divide space into 8 different regions. And those different regions are called octants. This is sort of a parallel to how we talk about quadrants in the XY plane. So when we're in space, we're now talking about octants. And what the question's saying here is that we want to restrict ourselves to the first octant, meaning just to the region where X, Y, and Z are non-negative. So as long as we keep in mind in this problem, we won't have negative x, y, or z values. That should lead us to making the correct sketch. All right, so the first couple things that we're going to want to do in this problem is we're going to want to sort out what is our region A and what exactly is the formula for our surface Z. So before we do those things, why don't we concentrate on just making a sketch of the plane. Let's see if we can identify a few points that lie on the plane. Quick way to get some points. I'm going to plug in values for 2 of the 3 variables, and we're going to get the value for the third variable from looking at our equation here. Remember that the governing equation is that x plus y plus z have to add up to 2. So if x and y are both 0, z would have to be 2. So that point is guaranteed to lie on the plane. Another point that might lie on the plane, let's keep things easy by letting x and z be 0 this time. Y would be forced to be 2, because again our 3 variables have to add up to 2. And a third point that lies on the plane, that should be enough to complete a sketch. Let's draw our x, y, and z axes. I'm going to mark off 2 units along each of the axes. Okay, and let's label our points. So 0, 0, 2, that would be up here. 0, 2, 0, that's got y component 2, the other components are 0. And then 2, 0, 0 with x component 2, there we go. Okay, so there are our 3 points. So the idea is that the plane actually contains this triangle here. Remember that a plane is an infinite surface, so the plane is actually bigger than the triangle. If I were to sketch it briefly here, so the plane is cutting through space like this, but it's going to be more helpful for us just to visualize that triangle and to understand that that triangle is part of the plane. So let's go back to the cleaner version of that sketch and let's see if we can now identify in the picture the region A and the surface Z that we're going to be working with. So the region A is part of the XY plane. It's actually that triangular base that we're seeing here formed by the x-axis, the y-axis, and then one of the sides of that triangle. So that is our region A that forms the base of our volume. Okay, now the surface Z that we're going to be working with is actually the triangular face, the triangle that is part of the plane. So I'm going to shade that part in very lightly just so we can distinguish it from the base. So hopefully we can visualize this in 3D. We've got a triangular base that is our region A, and then the surface that's cutting through space is this plane, and it intersects the x, y, and z axes in such a way that it's creating this triangle here. So let's label this, that's our surface Z. And we would like to find the volume under Z and over the region A. Okay, so let's call that discussion there step 1, where we sketched the big picture and identified our region A and our surface Z. So step 2 is going to be to specifically understand the region A. Let's sketch the region A. Now we're going to bend our minds a little bit to visualize this region. And the reason is I want to now concentrate just on the XY plane. So forget about what's going on with Z. Let's just understand what that region A looks like in terms of the XY plane. So in our picture here, we're just going to be concentrating on the base of this triangle. And let's try to figure out how that triangle would look when we drew it in the XY plane. Okay, well, these boundary points, the vertices of the triangle, will be super helpful in making this sketch. So what are the vertices of the triangle? Well, one of the vertices is at 0, 0, 0. So in our XY plane, that's at 0, 0. Okay, and then the other two vertices, we've got a vertex when x is 2 and y is 0. That would be here. And then we've got another vertex when y is 2 and x is 0. So there we go. All right, so this triangle here, that's our region A when we just look at it from the perspective of the XY plane. So if you were looking at this 3D sketch here from above, looking down on the XY plane, and if your axes were oriented correctly, this is the picture you would be seeing. Great. Now what we want to do is we're working towards coming up with the limits on the double integrals. So we need to come up with a way of describing this region A that we've just drawn. And in order to do that, we're going to need to get the equation of this line here. Let's work on the equation of that line. So best place to start, y is going to be mx plus b. And let's think about our slope here. So slope is rise over run. If we look at this line segment here, the rise is -2. We're actually losing 2 units of height. And the run is 2. So rise over run, -2 over 2. All right, so that allows us to conclude that our slope is -1. I'm just going to write -x plus b. Okay, and next thing we need to do is find our y-intercept. So y-intercept from our picture, that would be 2. So there's the equation of our line. Y is equal to -x plus 2, or that would sound a lot more natural if we write y equals 2 minus x. So I'm going to redraw this sketch just super quickly here so that we've got a clean version of that sketch. What we now want to do is we want to come up with some constraints on y and x, and these are going to lead us to the limits on the double integral. Okay, so thinking back to the beginning of integration, let's think about how we would consider integrating or consider calculating the area of this region. So the typical way to do it would be just to take some vertical slices through this region here. And we'd ask ourselves, well, what are the top and bottom points of these vertical slices here? So at the top, remember this equation here is y equal 2 minus x. At the top, our y value is hitting 2 minus x, and at the bottom, we're hitting the x-axis here, which has a y value of 0. So these y values are ranging between 0 and 2 minus x, and at the same time, the x values are running from 0 over 2. Remember this point was 2, 0. Okay, so x is ranging from 0 to 2. That's how we build the limits that are going to go on the double integrals. And again, just to reiterate, that process is very similar to the idea of taking vertical slices that we did way back when we were computing areas by integration. So let's see where we're at so far. We've made a sketch. In step 1, we made a sketch of our situation so we could get an overview, and in step 2 we sketched the regions. What that allowed us to do was come up with the limits on the double integral. So now step 3 is going to be to get a formula for z.